Welcome back, students. Lesson 16, we're in video part E. Important video. This one really gets to the heart of what the heck is a hypothesis test. You have to remember, students, we're trying to analyze a population, make a decision about some characteristic of a population. And we're only taking a sample of data. What if my sample doesn't jive with the whole population? What if I got unlucky data? Couldn't my hypothesis test results lead me to make the incorrect decision? And the answer is yes. Think about the one little analogy I'll give is, suppose you get tested for a disease. Say it's lupus or HIV or hepatitis or something. 4 things can happen with that test results. Either you have the disease or you don't, right? You're either healthy or you have the disease. If you're healthy, the test result could say that you have the disease or that you don't. That's 2 options, right? That's 2 outcomes. If you have the disease, you take the test at the doctor's office, you still could get 2 results, right? The test could either say that you're healthy or that you have the disease. So with a hypothesis test, sort of the same 4 things in essence can happen. One of the 2 hypotheses is going to be correct, and then we'll either fail or either we'll reject the null or we'll fail to reject the null, leading to 4 possible outcomes. So let's do an example just to see this through. And then once we get through this video, every time we run a hypothesis test, in the back of our minds, we're going to think to ourselves, I may have made a mistake. Hopefully chances are very small that we've made a mistake, but that possibility will be there. All right, making errors, here we are. It's going to be, yep, right at the top of the notes. Whenever you run a hypothesis test, you can make a mistake. This is because you're using a relatively small sample to make a decision about a relatively large population, right? Sometimes the data that we collect, just by the whole process of taking a random or unbiased sample, won't jive with the population. The data will misrepresent what's really happening in the whole population. In other words, we kind of just happened to be unlucky when we collected our data. Even if we thought through and had the best data collection plan in the world, got a completely simple, random, unbiased sample, we still could get unlucky. Problem is, students, we actually won't know if we got unlucky. We'll make our decision and then, hopefully chances are slim to none that we made a mistake, but we won't know if we did or we didn't. We just have to be aware of that possibility. All right, here's the example. One thing to keep in mind, this whole lesson 16, videos A up to F or Q or wherever, how far we're going here, are all proportion problems. But this example, I like it to talk about errors. This is a problem about means. In about 2 lessons, we're going to switch gears and do a couple of whole chapters on working with means. This is a mean problem. Don't let it confuse you, but you can handle it. Suppose we work for Consumer Reports magazine. And next month, the plan is we're going to recommend these Continental DWS tires, dry, wet, and snow. We're going to recommend them as a good buy unless there's compelling evidence, unless there's evidence that they don't last as long as the company claims. If you go on TireRack.com or wherever and you pull up these tires, you can see that there's a 50,000-mile warranty. And so I guess that would be the average tread. If you buy these tires, on average, we would expect them to last 50,000 miles before you would need to replace them. We're going to buy 20 tires in total from various online outlets. So I don't know, maybe we'll get 1 set from Tire Rack and another set from somewhere else. Altogether 20 tires, and we're going to run them out on our testing equipment. Remember, we work for the magazine. We're just doing our due diligence before next month's magazine comes out. Run a little test. In reality, 4 scenarios can happen. Okay? Now let's draw a diagram of the population and the sample. So here's the population. It's big, right? Big, I mean, really big. All right, there's the population. And you got to think, like, remember the who and the what, like, what's the who for this problem? It's tires, right? We're testing tires, we're collecting data on tires. The population size, I'm sure in production, sitting on shelf somewhere, there are thousands of these tires. We're going to be making a recommendation about the tires, about the whole population, right? Now, we're working with means, so there's a number I could use. It's the average for these thousands of tires. I'll put mu here. Working with means. Don't put P for proportions, put mu for means. And mu would be the average tread life. Or the mean tread life for these tires. And let me ask you a question. Do you know the average? The answer is no way. Think about this. Just because Continental's claiming 50,000 on their warranty, does Continental know the true mean value of their tires? Of course not. They would have to test every single tire to get the value of that. So this is an unknown number. What are we going to do at Consumer Reports? We're going to take a sample. Now, the budget says we've got enough money and time to look at 20 tires. So lowercase n, going to be 20. Once I have those 20 tires, what are we going to do? We're going to run them on our testing equipment, and I will calculate the mean. For a sample, the symbol's y bar. Remember these from a little bit ago? Sample mean y bar, population mean would be mu. That number I would know after I run my test, right? And this would be the mean tire tread from this sample. I don't know what the number is. Could be 48,222, could be 56,999. You just, once we actually do this, this is what's going to happen. Why could we make an error? Because the data we collect might not be consistent with the whole population. Okay? So, move on to the next page. Part B, let's see, flip it over. Yep, write down the hypotheses. All right, get rid of this big old picture here. H sub 0 for the null, H sub A for the alternative. We're testing means in this problem. It's the one single example in this chapter that we're testing means, so we'll put mu there, a little preview of what's to come. What are we looking for evidence for? Remember, the alternative is the one that we're looking for evidence, and we're going to recommend the tires unless there's evidence that they don't meet that warranty. So the alternative is mu less than 50,000 miles. If the data shows me that the mean is looking to be less than 50,000 for all of them, then we don't recommend the tires. Up top, what are we presuming? We're presuming that Continental is making a valid claim. We'll presume they're telling the truth. We're going to check by running the test, but we will presume that the mean is, let's just say, equals 50,000 miles. And again, in parentheses, I'm going to write this. It's not part of the answer, but this is presumed true to start. Might as well take Continental at face value that they're telling us the truth. One comment I made 2 videos ago, is Continental really claiming that the tires last exactly 50,000 and then they're trash? They're saying at least, right? They last at least. So in our heads, we might be thinking greater than or equals to up here, but in an undergraduate stat class, typically you just put the equal sign for simplicity. Okay, so those are the hypotheses. All right. 4 things can happen. Here they come. Scenario number 1. The null hypothesis is true. Nothing in our sample refutes it. In other words, the sample is consistent with the null hypothesis. Let's read this out. Continental has made a correct claim. The tires last, on average, at least 50,000 miles. the data that we collected, Consumer Reports, is consistent with the claim. For example, we took our sample of 20 and the mean turned out to be, oh, it didn't get copied or pasted in here. Maybe the mean turned out to be, let me see what I got written in the notes because it's in your notes, 51,558. I mean, that's in the notes right there. So we took our sample of 20 tires and the mean turned out to be 51,558. How on earth could we possibly reject the null, right? Which hypothesis is true? The null. So H sub 0, that the true mean really is 50,000 miles, is true. We collected our data. The mean was over 50,000. How could we possibly not recommend the tires? Based on the data, what's our decision? We would fail to reject the null. We recommend the tires in the magazine. Everybody's happy. Continental's made a correct claim. The data was consistent with that. This is a correct decision. So out of the 4 possibilities, at least one of them is correct. That's good, right? We're hoping our hypothesis tests will give us correct decisions, and this is one instance where it would be correct. All right. Pause the video, make sure you understand the first one before moving on to 2, but here I go. Scenario 2. Null hypothesis is true, but we sort of got an unlucky sample. So on this line here, which hypothesis is true? Again, H sub 0, that the mean mu equals 50,000 miles. Let's see. Continental has made a correct claim, so the 50,000 is valid. Our sample of 20 tires at Consumer Reports had an unusually low sample mean. For whatever reason we obtained, and it looks like that didn't get copied in there, but it's in your notes, right there. From the 20 tires, we got a sample mean of 45,110. Really unlucky sample. If we took a random sample, this was pretty unlucky. If you ran through the hypothesis test, this data was compellingly low enough, compellingly below 50,000 to cause us to reject the null, right? This was so below 50,000 that we don't recommend the tires. Problem is, we made a mistake based on data that was not consistent with the claim. We got that unlucky sample. Once in a while, you'll get one of these weird ones. This just happens to be one of those times. Based on the data, what's our decision? Common sense tells us this is so low compared to 50,000 that if you ran through the official test, which we will in a couple of chapters, we'd end up rejecting the null. Compellingly below 50,000 from the data. This is an incorrect decision. This is what's called a type 1 error. What did we do? We rejected the null when we shouldn't have. Got an unlucky sample, rejected the null when we shouldn't have. Who's going to be mad? Consumer Reports? Now, Continental Tires, right? They have a valid claim, they have a good product, and we just got this weird, unluckily low sample. We rejected the null, and they don't get the recommendation in the magazine. So with hypothesis testing, this sort of thing can happen. You have to be aware of it. I don't want you to get the sense that it's like a coin flip, like, oh, 50-50. Either I'm right or I'm wrong. That's not the case. If you collect good data and enough data, the odds won't be 50-50. The odds will be in our favor. All right, so what do we got here at the bottom of the page? Let's read through this. We made that mistake. We rejected the null even though it was true. Continental won't be happy with us. They should have gotten that good recommendation, but because of our unlucky random sample, they didn't. This is sort of an unfortunate result. It's a consequence of making decisions about a whole population based on incomplete information, which is just that sample. Okay, so that can happen. We'll flip the page, we'll look at the other side of the coin here. Scenario 3 of 4, now the alternative hypothesis is true. So right on this line here, which hypothesis is true? In reality now, H sub A, the mean is actually less than 50,000 miles. This is reality. Continental's made a false claim. Could you ever imagine a company making a false claim about their products? Of course. Probably happens more frequently than we'd like it to. So scenario 3, the alternative is true, and the sample was consistent with the alternative. So let's see here. I'm guessing something probably didn't get copied over. And so for part E, Continental's claim that the tires last at least 50,000 miles is simply not true. Our sample of 20 tires indicated the same thing. The sample was consistent with the alternative. For example, the data we collect has, and in here it says what? Y bar equals 45, 653. So pretend we collected 20 tires at random and we got that sample mean. Well, what are we going to do? Based on the data, we would reject the null, right? That's common sense is sort of feeling like, well, that's way below. Based on the data, we would reject the null. Consumer Reports magazine, that's us. We don't recommend the tires. We properly don't recommend the tires. This is a correct decision. Statistically, we've done the right thing. From Consumer Reports magazine, we've done the right thing. Should Continental be unhappy with us? Not necessarily so. I mean, basically they're making a false claim, right? Maybe we've discovered something wrong in their manufacturing process. Maybe they can correct it, fix the problem, and when we do tires next year, possibly they can get that recommendation. All right, so that's a correct decision. Might be a slide squeezed in here. Nope, goes right to 4. And we got a little something missing there at the bottom. Let me... Yeah, but that might be the lucky trick to make this work. Scenario 4, part F. One little thing got cut off, I think, on the last slide, but it's in your notes there. The alternative hypothesis is true. We just happen to collect an unlucky sample. Sort of unlucky in the other direction. So let's see, which hypothesis is true? We're saying the alternative, so H sub A, mu less than 50,000 miles. So in reality, the Continental claim incorrect. Continental's claim is untrue, as the tires don't last the reported 50,000 miles on average. This time, however, the sample of 20 tires had an unusually high sample mean. Oh, and here it goes. It's in your notes. Maybe we got Y bar equals 50,103. That's above 50,000. How on earth could we possibly reject a null if that's above? We're testing for evidence below and we got a sample above. You can't reject it. There's no way. Right? You need to be convincingly below to even start thinking about rejecting. With the sample mean exceeding 50,000, there's no way we can reject. We recommend the tires in the magazine. Maybe this happened by sheer bad luck. Maybe this happened because whoever we bought the tires from knew we worked for Consumer Reports, so they picked the best, shiniest looking tires to send us. I mean, could you imagine that ever happening too? Now, we're hoping it's just an unlucky random sample, but something could have got cooked up here. Based on the data, what's our decision? This is failed to reject. H sub 0. And down here at the bottom got cut off, but it's in the notes. This is an incorrect decision. I'll slide it over here. All right, that last bullet point on part F, this is an incorrect decision. And this one is what's called a type 2 error. 4 things. If we go back to that disease testing, the correct decisions would be what? I'm healthy, and then the test comes up negative. The test says I'm clean of the disease. That's correct. The other correct decision would be what? I have the disease, and the test says that I have it. Correct. Now there's 2 incorrect decisions, right? I'm healthy, but then I get a false positive. False positive, I take this test and it says that I have hepatitis when really I don't. That's sort of a stressful time, right, as you're getting retested. Hopefully come back clean the second time. And then what's the other one? You have the disease, you go get tested, and the test comes back negative, says you're clean. Incorrect decision. You can maybe think in your head, like some of these incorrect decisions might be costlier than others, right? If you have the disease, you certainly want to get diagnosed as quickly as possible. All right, so down at the bottom, part G, and then we'll wrap this one up. Summarize in general what can happen. And so let's put a little table with the 4 possibilities. Up top, we'll put reality. So here's reality. In reality, one of the 2 hypotheses is true. Either HO is true, that's the null, or the alternative is true. It can only be one of 2 things. And by collecting our data, we're trying to see which way the data is pointing us to make that decision. Down here, 2 things are going to be, here's your decision. This is after you run the test, you're going to make that decision. And what will you do? You'll either reject the null or fail to reject. And yeah, let's put reject the null up top, and then down below would be fail to reject. Two are correct. 2 are those errors. All right. So let's think about, get the correct ones up first. If I reject the null when the alternative is true, good job, right? This is correct decision up here. We reject the null when the alternative is true. And then the other correct one goes down here. If I fail to reject the null when the null is true, again, good job, correct decision. These are your 2 errors. The type 1, rejecting the null when the null is true, that's the type 1 error. Almost think of this as a false positive, right? Your data's convincing you to change your mind when it shouldn't have. It's a false positive. Down in the bottom is that type 2 error. Failing to reject when we should have, right? This is a type 2 error. And you can think of this like a false negative. You have that disease, you got tested for it, came back clean. Right? It's a type 2 error. Okay? So, what we'll learn in future lessons is this. Say we decide to reject the null. Wouldn't I want to, I'm hoping that the chances I make an error are very small, right? Then we'll have confidence in our test results. Or say that I fail to reject. I want the chances of making that type 2 error to be very small. And there's some things that we can do in the data collection process and we're running the test to try to minimize the chance of making mistakes. Okay? So, I think that's about it for this video. Thank you for watching. We will see you in class.